Hello, it's Stat 135, Lecture 7. Last time we covered Section 8.4 and 4.6. We finished the MOM estimator using the delta method to find the standard error of the MOM estimator. Today we're going to start maximum likelihood estimator, or MLE, by hand and in R, and also we're going to explore equivariance. So what is the maximum likelihood estimator? So we start with some random variables. We get a joint density. We take some observations, which are little xi's, and we form a likelihood function where now, because the xi's are fixed, this is a function of theta. And the max value of this function represents the value of theta that maximizes the likelihood of observing your data, x1 to xn. To find the maximum of the likelihood function, you would take the derivative and set it equal to 0 and solve for that theta. Doing so will involve the product rule. So, well, that's kind of an intractable problem unless your xi are IID. But even so, then it involves a product rule, and it'll be better for us to take the logarithm of both sides of this equation, turning that product into a sum, and noting that if theta hat is the value of theta that maximizes the likelihood of theta, then theta hat is also the value of theta that maximizes the log likelihood, since log is a monotonically increasing function. So I have a picture here to illustrate what I mean. So, taking the log, we get a sum of logs, and we take the derivative, set equal to 0, solve for theta. So here's just a silly example. If x1 is Bernoulli p, so here we have a single observation, let's say, where x is either 0 or 1. The likelihood function now is p to the x, 1 minus p to the 1 minus x. And so f1 given p is just p, and if f0 given p is 1 minus p. I've drawn these likelihood functions here, and you can find the ML estimators for each likelihood function. It's 0 when x is 0, and it's 1 when x is 1. So the maximum likelihood estimator is whatever x is. So it's just x. So here's another example. Say x1 to xn is IID exponential lambda. So here is the likelihood function, and we factor and then take the log likelihood, which we'll call L of lambda, and take the derivative of the log likelihood, set it equal to 0, and solving this for lambda gives us the maximum likelihood estimator of 1 over the sample mean. Here's another example, a function we've seen before. Consider an IID sample random variable with density 1 over 2 sigma exponential minus the absolute value of x over sigma. We want to find the ML estimator. So again, we follow our steps, find the likelihood, log likelihood, take the derivative, set it equals 0, solve, and you see that we get an answer different than the method of moment estimator, which I'll abbreviate MM, that we found before. Here's an example out of your book for a gamma distribution. This is 2 parameters. So the log likelihood is a function of alpha and lambda, and I've written a formula in yellow here for what we want to optimize. Using our log rules, finding partial derivatives, setting them equal to 0, and solving 2 simultaneous equations, you get lambda hat as a function of alpha hat, and unfortunately, using the second equation or using the first equation, we can't get a closed formula. So we're going to have to solve this numerically. And so we did an in-class exercise on B courses, where I took data from 227 storms in Illinois, and I formed a data frame. So here's a graph. It looks gamma to me. And so to do, we're going to essentially do Newton's method here. And so you need an initial point. So we used the method of moment estimator. We had a formula for this from earlier. We write a function, which is what we want to, in this case, well, we want to maximize it. The optimization program in R finds a minimum, so we take minus the sum of this formula, highlighted in yellow. And I encourage you to look at the help pages for Optim. Question mark Optim will, in the console, will give you information. So outspits the parameters that we want, the alpha and lambda, that are the maximum likelihood estimator. I should mention that Optim has several different optimization parameters, and the one that's like the Newton method is BFGS. I actually didn't use it here. I think I used the default, but it worked fine. But BFGS is lightning fast. So notice that the ML estimates here are similar but different than what the MOM estimates were. So we move on to the property of MLE estimators called equivariance. So here, this is a super useful property. For some reason, it's not proven in your book, but here it is. So it says that if you have an ML estimator of theta, and G is a function, not necessarily monotonic, then an ML estimator of G theta is G theta hat. That's so easy. So if you know an ML estimate of theta, and you take any function of theta, you don't have to go and recompute the ML estimate of that function of theta. It'll just be the function of the ML estimate. How easy is that? So the proof of this is really quite simple. So let's call phi G of theta. So G is not necessarily 1-to-1. So G inverse phi, which I call the preimage of phi, is not, can have several values, okay? It can be a set. So here's a picture. I have theta, the first line, I have a coordinate change under G to phi, and phi can be many to one valued. Phi may not be a function. I mean, G inverse is not a function. So phi, for example, can map to theta 1 and also to theta hat, to the MLE estimator, for example. So, but how I'm going to define a likelihood function for phi, I've drawn here the likelihood function for theta. How I'm going to define the likelihood function for phi is so L, when I write L phi, there are many possible candidates. Like you could imagine it being L theta 1, or it could be L theta hat, right? But I'm going to take L of phi to be the maximum of all those possibilities, which in this case would be L theta hat, right? So So L of phi is the maximum of L theta over all theta in G inverse phi. So to be the likelihood function, so now notice that L phi is as large as possible, right? It's the maximum. So obviously if G inverse phi contains theta hat, as it does in this example, then L of phi is greater than L of phi prime for any other phi prime. So any other phi's, L of phi is going to be greater than or equal to it, because L of phi is L of theta hat, and that's as large as possible. So so G of theta hat is phi hat, which is what we had to prove. And okay. Well, I wrote another proof here, but it's all the same. So here's just an example. Say x is Bernoulli theta, so the exponential of x is theta, so theta is a parameter of x, and the variance of x, which is theta 1 minus theta, is also a population parameter of x, right? So let's call that phi. Okay, so phi is G of theta is theta 1 minus theta. Okay, and so what I'm going to show is that phi hat is theta hat times 1 minus theta hat. That's the equivariance property. So we're just going to concentrate on one of the likelihoods, the one with x is 1. So here's the likelihood drawn here for x is 1. So this is L theta. So this is the likelihood of theta. And notice that as theta runs from 0 to 1, phi runs from 0 to a quarter. So, and furthermore, G inverse is many to 1, possibly, because G of 0 maps both to 0 and to 1. Clearly 1 is the MLE estimate for theta. And we're going to show that 0 is the MLE estimate for phi, and so you can see that that's the case here, right? Because 0 maps to 1, and 1 maps to the max. So G, now G isn't a monotonic function. The likelihood of phi can take more than one value. So the likelihood of phi is right. So the likelihood of phi, well, I should just say here, I wrote a little bit too much here. So we define the likelihood of phi to be the maximum of as theta runs over G inverse phi. So in this case, so we're choosing our theta in G inverse phi that maximizes the likelihood of theta. So since theta hat ML maximizes the likelihood of theta, as I said earlier, G phi hat is G theta hat, and that maximizes the likelihood of phi. So this will be a property that we'll use many times over, and I'll see you next time.